countries, one from Japan, another one from UK. And he started as an independent researcher to start with in IIT Kharagpur. Now he is an assistant professor there. He is also a recipient of Ramanujam Fellowship.
Yeah, thank you for the generous introduction. And good afternoon, everyone. I'm the one who is stopping you from lunch. So I work on nickel catalyzed oxidative cyclization of pi systems over benchtop. Firstly, I would like to thank the organizers to give me an opportunity to present my work here. So I joined the institute in 2018. So I'm going to present some of my work that we have been doing recently. So the main aim of our work is to bring nickel catalysis to the benchtop. You know, nickel is very sensitive in the presence of air and moisture, but the main idea is to bring it to benchtop and make it easy to access. So, sorry. Yeah. So our work mainly focuses on multifunctionation of unsaturated systems. So we work basically on nickel mediated reactions, and these are the verticals: copper and phosphorus catalyzed reactions. And so today I'll be talking about our nickel chemistry here. So we mainly focus on the oxidative cyclization of nickel zero with pi systems. So what we are doing here is we select two pi systems and then we add nickel in a 2 + 2 + 1 fashion. So this gives us a 5-membered nickel species. Yeah. So in the first example, we have an aldehyde and an alkyne. So when they do cycloaddition, we are going to get the corresponding allyl alcohol. And similarly, when we have aldehyde and an enamide, we are going to get an enamide sort of system here. So today I'll be covering these three topics. If possible, I'll also show some of the results from here. Right. So when I joined in 2018, and I applied for funding. It was about 2019. The time we placed an order for a glow box, COVID happened. And for the 3 years, we are not able to get glow box. So now the problem is, I have proposed, my proposal is based on nickel zero, and I don't have a glow box. So what should I do with it? So, so the thing is, I started looking at alternative ways of accessing nickel zero. So these are famous air-stable nickel zero complexes that has been recently developed. So this is the famous one, nickel COD2, which is highly air sensitive. It decomposes in 1 hour in air. So if we replace one of the COD ligands with electron deficient alkenes, generally what happens is this becomes much more stable. So what we're trying to do is we're trying to remove electron density from nickel zero so that it becomes more stable. Yeah. So here they have used a styrene. This is Cornella's work, and Engel. This is in 2021. So they have used a fumarate ligand, and this catalyst here, this complex here, is very old, 1962, but nobody has used it in catalysis much. It is very less explored. This is called nickel COD DQ. This is duroquinone. These can be easily prepared. All these catalysts require glow box for preparation, but this catalyst, we don't need a glow box to prepare. So what we can do is we can take nickel COD and add DQ. DQ is this duroquinone part, and then heat it at 45 degrees Celsius. We get this red powdery material. This is almost equivalent to sodium sulfate in our lab. We store sodium sulfate in the lab. So this is a nickel zero system, but we can easily store it in air for almost 200 days. So there is no problem with this catalyst. This can also be prepared through a glow box free method, where we start with nickel acac, reduce it in situ, form the nickel COD in the Schlenk line, and then we add DQ to it. So this will give you the same complex. Yeah. So now we have the complex ready. So Aki is a PMRF fellow. She took up this challenge of using this complex for oxidative cyclization. So here you can see that all the aldehydes and alkynes that we have, they give very good yields and selectivities. So the selectivity depends on the ligand that we use, basically. Since our ligand is NH3, so most of the times the selectivities are constant. It's 97.3 in all the cases. So similarly, we can use alkynes and enamides. The enamides also provide very good selectivity here. And this is a chiral substrate which comes from chiral oxazolidone sort of system. and we get very good diacetyl stability in this situation, right? So now the question is, the catalyst is very stable, that we know. So that means the reaction is also going to happen in air and water, is what we asked this question. So what we did was to look at the catalytic activity. So catalyst is giving us 81% when we prepare it freshly. So we store it for more than 200 days, the catalytic activity is still maintained, 79%. There is no issue with the catalyst for more than 200 days. You can store it like sodium sulfate on top of the bench. But when we open the reaction to air, there is no reaction. Similarly, when we do the reaction in trace amount of water, there is no reaction as well. So here, what happens is, we also tried to see what are the byproducts, what are the products that we are getting out of the reaction. One of this is duroquinone here, so which is the ligand that we actually added. So in this case, during the reaction, the duroquinone decomplexes, makes the active catalyst, and you can see here, when we add nickel COD-DQ with NHC, we are getting the corresponding NHC-DQ complex, and when we add the substrate displaces the DQ. And this complex here is highly air sensitive and moisture sensitive. So the reaction is highly air and moisture sensitive still, but the pre-catalyst that we have is quite stable in air and moisture. So this is the mechanism here where this 2 plus 1 adduct will give us the corresponding 5-membered ring, and this undergoes metathesis, sigma 1 metathesis with silyl hydride to get the corresponding allyl alcohol, silyl allyl alcohol. So this is a simple comparison between nickel COD and nickel COD DQ. This is very few hours, it is stable in air, but here it can stay up to 200 days, not a problem at all. And storage and handling, this requires glove box, and it should be stored at -20. You need a freezer with the glove box, but here it requires, it can be stored on the bench top. The functional group tolerance is good with nickel COD, but it is much superior with this catalyst here. Yields are good and comparable and superior than nickel COD. Reaction time, nickel COD2 is short. Since we add DQ, we are sort of removing electron density from the nickel. So what happens is the activity comes down. So because of that, the reaction time is a bit longer. And the cost of nickel COD is expensive, and this is also expensive as well. So we are not working on the cost side of it, but it becomes more stable over the bench top. Yeah. So what I've shown here is these two examples here. So my student was trying some other work with 1,3 diines. So, and he forgot to add the aldehyde, okay? So what happens in the situation? He got a very nonpolar spot, and then we tried to characterize it. What we found was it underwent a cyclotrimerization of this type. When it undergoes cyclotrimerization, you get a hexasubstituted benzene. This is all substituted benzene, fully substituted benzene. Yeah. So hexasubstituted benzenes are very important because the Taxol core is hexasubstituted benzene, and here there are several optoelectronic materials which are highly conjugated hexasubstituted benzenes, and you can also have host sort of supramolecular materials which are also a part of which consists of hexasubstituted benzene as well. So we looked up the literature. So with 1,3 dienes, only one report was known with copper catalyst, and the problem is that it is very much restricted to aryl alkynes, aryl substituted alkynes. The alkyl ones don't work, so this is restricted to aryl dienes, and they have very poor selectivity. The selectivity that I mean is this is unsymmetrical substituted, and this is symmetrically substituted hex-substituted benzene. Okay, so what we thought was if we want to accommodate alkyl functional groups, the catalyst has to be more reducing. So if we compare cobalt 1 and nickel 0 is more reducing than cobalt 1. So what we thought was to use nickel bromide as a pre-catalyst and reduce it in situ with manganese to form nickel 0. And this can now trigger our 2 plus 2 plus 1 cycloaddition followed by another Diels-Alder type reaction to give us the corresponding hexasubstituted benzene. So we made a lot of substrates. You can see here the alkyl substitutions work very well. We can scale it up to a gram scale, and we can have several alkyl substitutions, chloro, free hydroxy group, ester, cyano, all works pretty well. And it is also compatible with aryl functionalities. So we took one step further. Can we substitute sugars and make like multivalent sugar compounds on benzene? Okay. So these are lectin binders. So they bind, lectins are specifically going to bind with carbohydrate fragment. So what we did was to prepare the corresponding 1,3-diene with glucose, fructose, galactose, and mannose. And we showed that all these couple to give us the corresponding hexasubstituted benzenes with sugar decorated on the peripheral. And they gave pretty good yields as well. Now the story is both the ends are symmetrical. What happens if these two are not the same groups? So theoretically, there are 8 possible combinations that you will get as a 8 series isomers, 8 isomers you should be getting. So let's say if I take the first example, where this is phenyl and butyl in these two ends, I can have 8 possible combinations. And when we do this reaction, we get all the 8 possible regioisomers. So it is very difficult to control this reaction. So what we thought was to bring in some stereoelectronic effects in those reactions. So we started to introduce bulky groups. A terbutyl group. A terbutyl group will never like to be in this position because it is going to have a lot of steric hindrance. So it will always try to be in the peripheral of this alkyne. So we can clearly see that there is a single regioisomer with greater than 95 to 5. Similarly, if we add silyl groups, the silyl group also provides pretty good selectivity. Now, what about the electronics? So if we substitute it with aryl and an ester group, aryl and ester group, generally the ester substituted double bond is electron deficient. So they are going to preferentially, the nickel is going to preferentially add to the electron deficient double bond, triple bond basically. So the ester functionality is going to get in, and so this is going to be here, and the aryl group will go to the periphery. So this is how the stereoelectronic effect of this reaction generally works. So we have very good selectivity in these cases as well. Fine. So if we look at the mechanism is very complicated. As you can see that there are several pathways involved. We actually did the calculations, but I'm not going to go through this. But I'll present a very simple sort of mechanism here. So where we form the nickel 0, and then this coordinates with the triple bond. So this does a 2 plus 2 plus 1 oxidative cycloadation to give this sort of an intermediate. So there are 3 possible intermediates that we can get, and only one of them will go further to react to give us the hexasubstituted benzene of this type. So, but the situation is pretty complex when we consider all the pathways. So, yeah, so this brings me to the end of this section. I'll just briefly tell you what we are trying to do here. So here we had aldehyde and alkyne, and here without alkyne. So here what we are trying to do is we are trying to add aldehyde and alkene. So aldehyde and alkene are very difficult to add because alkene's pi star orbital is pretty high. It is very difficult for the nickel to access this pi star orbital. So because of this reason, we tried to do this reaction intramolecularly. So my student Srito here, who tried to do this reaction to get the corresponding chromanol derivatives. So these chromanol derivatives are very prominent in natural products. So the key intermediate is like where the nickel adds to these pi systems to form this 5-membered 2 plus 2 plus 1 adduct here as well. So, sorry. So what is the challenge in these substrates? What is new here is that generally in the literature, when we see that, here we don't have any heteroatom here. When we introduce a heteroatom, the metal adds to the double bond to form an allyl like a Sujitros type dealylation. So generally this is the side product that we get. So this is the main challenge to use these as substrates. So here what we have done is we tried to add a Lewis acid to increase the electrophilicity of this aldehyde so that this sort of 2 plus 2 cyclization happens in these cases. So with this, we have made several substrates, not going to go into this. So the synthesis of anti-asthmatic drug is what is shown here. So we use this intermediate, we use our methodology to make compounds of this type. So the mechanism is very similar in this case, where the nickel forms nickel 0, and it undergoes 2 plus 2 plus 2 addition to give us this intermediate, and this further opens up to give the corresponding chromanol. That's all. So totally, I've shown you that we can access these building blocks, all these 4, using oxidative cycloaddition reactions. So I'll stop here, and I'd like to thank my students. This is my group. Today I presented the work of Rajesh, Aki, and Sudipto is here. Yeah, so these 3. And I thank the funding body, SCRB and STARS and IIT Kharagpur for the funding. Thank you very much. Thank you all. Thanks.
Thank you. You have finished well within the time, actually. Okay. Any questions?
I think they are agreed.
Everyone understood everything.
It's fine.
Any question from front bench? No, everything is clear. Sad.
If somebody has to ask, I can ask this question. Of course, this is very, very interesting work with using nickel 0. And my point is very simple, that can we make it even more stable than what you were able to achieve 200 days kind of thing? And still there are issues with the air, there are issues with water.
Yes.
Can we make stable nickel complexes like nickel acac, for example? It's an extremely stable molecule. I also handled it. But well, you might comment on that, making it even more stable than what it is.
The problem with making it more stable is that it won't decomplex very fast. So we need the ligand to come out of the complex.
Like so nickel acac, for example, nickel acac is extremely stable, so it doesn't work at all.
The reduction capability of nickel will come down quite a lot. So nickel is superior than palladium because of its reduction capabilities. It can do oxidative addition very strongly. So so that
industry will love nickel, but they are forced to use palladium. That's the idea. Actually.
But palladium is robust. So
robust, but then palladium is very costly. But did you work on some hydrogenations on this kind of?
No, I have not ventured into hydrogenation. Mostly, we are focusing on cycloaddition reactions.
Good.
Thank you.
Okay, thank you.
Thank you, sir. Thank you, Dr. Ganesh. It's a token of appreciation.
Thank you.
Thanks. Thank you. So with this, I think we are ready for lunch. Enjoy the lunch.